So hello everyone, this is lecture 13 for the classical physics. In the last lecture we were discussing about the variation of G, that is acceleration due to gravity, and we discussed this first factor that was because of shape of the earth and as it was oblate. So we discussed that at equator it will be less and at pole it will be maximum because of this relation. Now let's see the other three. Means when one moves from the above the earth, means with altitude, how G varies. So as one moves equator to pole, he will observe the increase in G. So that was the conclusion of first one. So I am having a little cold, so please tolerate. So with altitude, how our G is gonna vary. So let's say first the our man or any object is at here, and it is experiencing the G value. We know at the surface, G is nothing but Gm over r square, and we call this point as A. Now it moves to the height at h to the point B. Now this height will be added, so G at B will be Gm over r plus h square. So we call it as GH. Okay. Now take this ratio GH over G. So when you will divide this one from this one, okay, means GH over G. So this one will be divided by this. So you will get this equation. From here you can find GH equal to G, and this r square will go into a denominator, and it will give you this factor 1 plus h over r whole square. Now see, if your height is very large, then you will use this formula. Means normally you will always use this formula, but in the special cases when they say that height is very small as compared to r, very small as, as compared to r, so what we will do, we will take this to the numerator. It will be 1 plus h over r raised to the power minus 2. Then we use the binomial expression, take the first terms, so that will give you gh as g 1 minus 2h over r. Okay, so for small h this expression is true. So from this expression we can conclude that as h increases, our gh decreases. Okay, so this sign represents as h increases, gh decreases. So with altitude, value of g decreases. That's how our g varies with height. Now the third one is how g varies with the depth inside the earth. So let's say this is origin and this is a point. At this our value of g is g, and now our object moved to the depth d. So we need to find the value of g at this point. So g at a is nothing but same g over r square. We call it as g. Now at r, when this radius is nothing but capital R minus d, so small r is this, and we already find this term at the in the solid sphere, means the value of gravitational intensity at this point, and g is same as gravitational intensity. So at this point gm over r cube, this will be this, and this r is the radius of this. So now just substitute r as r minus d here, so this will be your value at depth d. Okay, now let's compare. For that we need to divide this one from this one. So let's see what we will get. GD over G will give you R minus D over R. Now from here GD will be G 1 minus D over R. Okay, so this is the expression for how our G varies with the depth. So you can see that again as D increases, this value decreases. So again going inside the earth, our D is also decreasing. So it will be maximum at the surface and it will decrease above and the below the earth. Okay, now you can see at the center d will be r, so you will get 0 value. So value of g decreases with depth. So now let's come to the fourth, that is due to rotation of earth. Now our earth is also rotating with the, means we are, then there is some difference in the g because of that also. So let's consider how this g gonna vary with that. So first let me give you an example so it will be more clear to you what we're gonna do here. Just like a lift, you are in a lift and it is moving downwards with the acceleration a. Okay, then natural gravity will be g. So what you will feel, what is the acceleration you will feel, that will be g minus a. Okay, because as a increases to g, you will feel the free fall, means you will feel the no force inside this gravity. That's why we write this expression as g minus a, because when this a becomes g and you are inside the lift, you will go up and you will feel the no force you will feel here inside the lift. And you can find this expression from here also, means force is mg downwards and net force will be, and the reaction force gives you the weight. So mg minus ma means mg minus r equal to ma. So from here you can find that r is nothing but mg minus ma. So m take common, g minus a will be your acceleration, net acceleration. So that's how you can find this. It will be g effective will be g minus a, because the net acceleration you are feeling, that is your g. Okay, so now remember, this a is nothing but the acceleration of this lift. Okay, and g is the natural one. So g effective, what you will feel inside the lift, this will be g minus a. So let's see how we can relate this in the earth. See, this earth is rotating, and we know it will rotate from west to east. This is west, this is east. So we'll have some angular velocity. Okay, and if particle is here, then naturally g is in downward direction to the center. But with rotation, this object is also rotating around this circle. So after rotating this circle, it will feel a acceleration toward this axis also. This is due to our centripetal force. Okay, so we have this acceleration also, and g is this side. So we have some net acceleration towards the center. So that will be our g effective. So let's find the value of that. How you can find? First of all, if rotation's angular velocity is omega, and this particle is rotating like this, and this is radius r, so it will be omega square r. This radially inwards, this acceleration will be omega square r. We know this from the formula, you remember, a equal to omega square x. So ar will be omega square r. Now we need to find the component means this radius r. We need to find actually the component of this acceleration towards the center of this earth. Okay, so that's how we will conclude. So to find that, first we need to find the relation between this r and capital R. So this, if this angle is lambda, then this also with lambda, then this r cos lambda will give you small r. So r cos lambda will be small r. So just substitute this r value here. You will get ar as omega square r cos lambda. Now you have the value of this acceleration in the form, in the terms of this r value. So now you need the net acceleration towards the center. So you need to find the this component of this vector towards this vector. Okay, so this is lambda, so it will be ar cos lambda towards this side. So it will be ar will be omega square this we already find. Now towards the center it will be ar cos lambda. And now towards the center we are having two accelerations, that is first is g and second is ar cos lambda. Okay, so this is the same condition like this. So net acceleration will be g minus ar cos lambda. So g prime will be g minus ar cos lambda. So that's how you get this expression. Okay, now you can just substitute the value of ar from here. We find it already, omega square r cos lambda. It will give you this expression, g minus omega square r cos square lambda. Now you can verify this expression as at lambda tends to 90. So at pole it should be maximum value. So at lambda equal to 90, this will turn out to be 0. So we'll get g prime as g. So this is our maximum value. And at equator we will have minimum value. So lambda is 0. So you will get g minus omega square r. So this will be your g minimum. With lambda, g is increasing. So as lambda increases, g will increase. So remember this. I hope this is clear to you. Now let's consider some questions. It will be more understood to you that which kind of questions are asked. So these are previous year questions actually. So radius of earth is approximately 6400 km. The height h at which acceleration due to earth's gravity differs from g at the earth's surface by approximately 1%. So we need to find that height at which the variation in the g is 1%. So we know with height it will always decrease. So variation will be means it will now become 99% of g. Okay, so 99, we will use the direct formula, g dash as g 1 minus 2h over r. So g dash is nothing but 99% of g. So use this formula, g will cancel out. You know what is r is given 6400 km. From here you can find the value of h will be 32 km. So this will be your answer. And here as h is in the very small range, that's why we use this formula. Let's see one more question. A period of oscillation of a simple pendulum at sea level and at top of the mountain of height 6 km are T1 and T2 respectively. If the radius of the earth is 6000 km approximately, then we need to find this T2 minus T1 over T1 is closest to. So see, there is this mountain and there is this sea. So at sea we consider it is equal to G, the value of G, and at mountain we need to find the difference. With height it will decrease. So there is a difference between the time period also, because we know for the time period of a pendulum formula is 2 pi root L upon G. L is the length of that pendulum and G is gravity at that point. So if G differs from those 2 points, so we see that time period also differs. So we'll find the both time period and find this ratio. Let's see. T1 is 2 pi root L over G. This is at the C, so we'll consider this G. Now at height H, T2 will be 2 pi root L upon GH. Now we know the formula for GH is G over 1 plus H over R whole square. So we'll use this formula. Here it will give you this. Square will cancel out with square root. So you will get this formula. GH is this, so you will get 1 plus H over R 2 pi root L upon G as T2. Now see, this is nothing but T1. So we'll write this T1 1 plus H over R. Now you can directly see that if you multiply T1 inside, you will get T1 plus T1 H over R. So you will get T2 minus T1 divided by T1 equal to H upon R. So H upon R is this ratio. So H is given 6 and R is given 6000. So it will be 1 upon 1000. So it will be approximately 10 to the power minus 3. So this ratio will be 10 to the power minus 3. Let's see one more example. There are two fixed heavy masses of magnitude m at high density, these mass m, on the x-axis at this point and this point, d00 minus d00. A small mass m moves in a circle of radius r about origin in the yz plane between the heavy masses. Find the speed of the small particle. So let's consider this is our x-axis, this is y and this is z. So these two heavy high density masses are places on the x-axis at d00 and minus d00. Now this particle is rotating in the yz plane. So we need to find that what is the speed of this particle with which it is rotating. Okay. So you remember from the circular motion that whatever is rotating, there will be a centripetal force it requires. So that centripetal force is nothing but mv square over r. This r is radius, v is velocity and m is mass. So there will be some force given by these two particles by which it is rotating. So we will equate that to the mv square over r and find the v. So let's see how. The force due to this one on this one will be F in this direction and F in this direction. So if this angle is theta, this angle will be theta. So toward the center it will be F sin theta from this one and F sin theta from this one. So it will be total force 2F sin theta toward the center. And these horizontal component F cos theta and this, they will be cancelled out to each other. So we'll get net force as 2F sin theta, which will put as 2 mv square over r. Now let's see. Mv square over r equal to 2F sin theta. From here we can find the v. So 2F is nothing but g mm over. So F is g mm over this distance square. This distance is nothing but r and this distance is d. So it will be under root r square plus d square. So it will give you r square will be, means the square of this distance will be r square plus d square. Now the sin theta you can find. Sin theta will be perpendicular over hypotenuse. So perpendicular is r divided by under root r square plus d square. Now from here you can directly find this v square value. Take this r this side and m will cancel out. So v will be this 2gm r square divided by r square plus d square 3 by 2 1 by 2. So this will be your answer. Now let's see one more interesting thing. Means there are many questions asked from this kind of thing. Consider it as an example. So it is in a hypothetical condition. Means we have earth and we made a tunnel which is passing through the center of the earth, and now we unrest a particle. Means we put a particle with mass m inside the tunnel at the distance x from the center. Now it will gonna have a simple harmonic motion, or it will gonna oscillate. So we need to find the time period and the frequency of this oscillation. So let's consider mass of the earth is m and r is the capital R is radius. So this is a solid sphere. So at any point x, we know how to find the gravitational intensity. I is equal to minus gm over r cube multiply this distance x. Okay, so we have gravitational intensity. Now we can find the force. Force is nothing but just multiply with mass to the I. So F is mi. Now I is this, so we get the force as this. So we can compare this force as ma. So from here we can find the acceleration as again this. So this is same as intensity. So acceleration we know for a simple harmonic or oscillator motion it is omega square x. So x is this distance. So let's compare omega square x to this. So we'll get omega square as this under root gm over r cube. Now omega is nothing but 2 pi over t. So that's how you can find the omega, and from here you can find the time period also. So this will be your time period. So that's how you can solve this question. So there is this one variation in this question also. Like now we are not tunneling in the towards the center or passing through the center. Now we are tunneling a tunnel which is not passing through the center like this horizontally. Now you put a particle here and you need to find the omega and time period. So let's see. First we need to find the gravitation intensity at this point to find the force. So see this distance, this is x, this is y, so this distance will be under root x square plus y square. So this will be just same formula, minus gm over r cube multiply x, and x is here this under root x square plus y square. So this is our intensity at this point. So force will be just multiply with m. Now see, we are having oscillation in this. This tunnel is frictionless. Okay. So now the force in this direction will give us the oscillation. So we have the force or the gravitation intensity in this direction. So what will be the gravitation intensity in this direction? So if this angle is theta, so this will be theta. So this cos theta will give you the acceleration. So cos theta is nothing but this b x over this. So x over this. So this will give you the intensity at the x direction. Now this will cancel out and you will get ix as minus gm x over r cube. Now force in this direction will be just multiply with mass m to this ix. So you will get this expression, and now you can compare it with the omega square x, because from here acceleration will be this sorry, this, remove m. So omega square x will give you, x will cancel out, omega will be again under root gm over r cube. So from here this is just same as we passes through the center, so we get the same expression. So it will be same for this also. Remember this point. Now we can find the time period if we have frequency. You know how to find. So there is this one more question can be framed up from here. This is like what is the force perpendicularly, normal force, what will be the normal force in the tunnel if there is friction. Okay, so how you can find? So this is nothing but find the acceleration, means the intensity, gravitation intensity, this component of this. So it was cos theta, so it will give you iy sin theta. So sin theta is nothing but this y over this. So here you will get y over this will cancel out. So iy will be minus gm over r cube y. So multiply with m. So you will get the force in the direction of y. So gmm y over r cube. So this will be your answer. Just like this. Okay, this will cancel out and this will give you this answer. So let's move to the new topic. I will just introduce you with this. We will see more detail in the next. So what is gravitational potential? Let's first see the definition. It is defined as negative of the work done per unit mass in shifting a test mass from infinity to the given point. Here we are assuming infinity as the reference point and potential is considered as 0 at the infinity. So what is it trying to say is that gravitational potential at any point P is the amount of work done on a unit mass from infinity to that point. Means the amount of work done was done to bring this point, in this particle or anything, a unit mass from infinity to this point. So that is called the potential at point P. Okay. Now see, because this is a attractive force, so this potential is always gonna be negative. Means at infinity it will be high potential and at this point it will be negative. And it's gonna be more negative toward this side. Okay. Because the gravitational intensity direction is always this side, high potential to low potential, we know that. So I is nothing but minus dv over dr. So this formula you will understand when we discuss about it. So you can relate this formula by, you remember from the electricity and magnetism, E dl equal to V. So this formula is just same. There it was electrical intensity, here it is gravitational. So it will be, so see, this should be negative because we already discussed that direction of I is towards the center radially inward. So we put this minus sign. So Now see, it is at high potential, it is at low potential, and so if we find the difference between this point and this point, the potential difference, this is A, this is B, so VA minus VP is positive, and dr, this distance is large, this distance is small, so this distance is also positive, so this quantity will be always positive. So see, but I is negative, so that's why we have to put a negative sign here, okay, to make this equation correct, so to have the direction for I. So that's why we have put in this negative sign, and this relation gives us this formula for the potential, means the amount of work done per unit mass to bring it to the point P will be potential, and this negative sign comes because of this reason. To satisfy this equation, we put negative sign here. You can see that from this formula we can get this formula again, like what is work done? Work done is nothing but this force into the displacement, so m naught I will give you the force dr, so m naught is constant, this will cancel out, so minus I dr is v. So see, integration of this will give you this, so it means differentiation of this will be equal to I, so here I is equal to minus dv over dr, so only that will give you v again. So that's how these two relations are correlated, and I should be negative, that's why we are getting negative here. So remember this point only, and we already discussed why I is negative, because it is radially inward, and potential is high at here and it is lesser at here because of attractive forces. Okay, so that's it for today. Thank you everyone.